Hello everyone, I am Priyaprakash Rahu and I am a final year student of the Department of Electrical Engineering, and today I am giving a presentation on my second bachelor thesis project on the topic ACT tolerant charge pump under the supervision of Professor Meghang Sharath. So before getting into what is an ACT event, first we consider what actually causes an ACT event, or as we can call it, a single event transient. So, in applications where there is a large concentration of high energy particles that we call radiations, like alpha particles in the space, uh, there can be various alpha particles that strike the PN junctions created by the active region and the substrate, leaving many atoms ionized as a result after striking them with their kinetic energy, and these released charges flow due to the reverse bias applied across the junction, and these uh, charges, when flown into the capacitance at the node or through a resistance present at the node, can cause the voltage of the node to get fluctuated, which can be a serious problem in some applications. So the purpose of the charge pump in our project was to be a part of the phase lock loop that provides a clock output that is 10 times as that of the clock input. And in this PLL loop, the charge pump feeds the current into the loop filter, which provides the control voltage to the VCO. And hence, the charge pump outputs should be very stable in order to avoid jitter at the clock output, which would otherwise get propagated to the subsequent digital blocks, causing errors like metastasis. Then we get into the basic charge pump circuit that we have used. So we have used two PMOS, uh, two PMOS transistors and two NMOS transistors at the bottom that form a cascaded stage for providing for sourcing or sinking current into the control node, and these are provided with appropriate biasing voltages from another stage. And then, as we can see, there is a PMOS provided by the up signal from the PFT and an NMOS provided by the down signal, which control whether the current is to be sourced or sunk into the node. But then we can also see there is a PMOS that is controlled by the up bar signal and an NMOS controlled by the down bar signal, which are there to tackle a problem called uh, charge causes charge sharing. So in charge sharing, what happens is that when the up and down signals are when the up and down switches are off, the nodes B and E get pulled to VDD and ground respectively, and hence when we subsequently turn on the switches, the charge stored into the node capacitances at the nodes B and E get discharged into the capacitance of the weak control node, which causes some fluctuations in the node voltage, causing jitter in the output clock. And therefore, we have this other part which gets closed when the up and down switches are open, and the op-amp connected in the voltage follower configuration makes sure that the voltages at node B and E, even in this ideal state, are at V control. And then, as we can see, uh, the effects of the strike are modeled as current sources either sinking or sourcing current, depending upon whether the strike occurs at the drain of the PMOS or NMOS, and they provide a fixed amount of charge, which correctly models the effects of a radiation strike. So this is the biasing circuit used by us in our project, where the highlighted resistance can be varied using various digital signals or switches which add or remove resistors in parallel and hence controlling the current flown into the charge pump. So, by decreasing this resistance, we can actually increase the current in the charge pump, which can be used to increase the gain of the phase lock loop, which helps in faster settling and faster response times to the output jitters of the charge pump. But there is a trade-off as the stability goes down when the gain of the loop increases. So now we come to the solution that we have proposed in our project. So in this, we are trying to tackle the strike effects at the most important and critical node of the charge pump, which is actually the output node of the main path of the charge pump. So we are splitting by the main path. We mean the paths including the up and down switches. So in this, we are splitting the main path of the charge pump into 8 parallel paths that are connected to the charge pump output via a resistance that does the work of isolating the nodes from the charge pump output, and each current source and switch is sized exactly 1/8 as that of the original charge pump sizes, and hence when an SET event occurs, it uh, it is expected that it only occurs for one path, and hence the intensity of the effect is about 1/8 as that would have been in the original charge pump, which is further mitigated by these isolation resistances in the output. So the resistance does the work of isolation due to its construction itself. So the construction of the resistance is such that there are no PN junctions in it, and hence no SET event occurs for the resistance nodes. Now we come to the results obtained as a result of our work. So earlier, as we can see in figure A, the charge pump output had very large dips and hence was not suitable for our work. But then, after installing the split paths, we can see that the output is fairly stable and practically ignorant of the uh, strike effect. This is the eye diagram obtained at the output clock or the PLL output when a strike event occurs. As can be seen in the first case, the eye diagram is very unclean due to very slow settling times, while in case of the radiation hardened charge pump, the settling is fast and the eye diagram is a lot cleaner. After this, we observed that strikes at the alternate path output was also causing a significant amount of deterioration in the output clock, and hence we decided to split the alternate path identical to the main path into 8 parallel paths, and as a result, we obtained very stable eye diagram at the output. Further, as we know, the op-amp output is also a common drain stage of a PMOS and NMOS, and therefore strike is possible at this node as well. So when we checked the effects of a strike at this output, we observed that although not much, but there was still some deterioration in the eye diagram at the output, and hence we had to look for strategies to mitigate this issue. This is a possible solution that we have come up with, where we split the charge pump, where we split the op-amp similar to the charge pump into 8 parallel paths, where the sizes are again 1/8 of the original sizes, and they are connected in parallel through isolation resistances. So this way, as is the case with the charge pump, the effects of a radiation strike become almost 1A as that in the original case, and the resistance also provides isolation from the output node. But this of course can cause some slowing in the response time of the op-amp, but that won't be an issue in our application as the V control voltage does not change rapidly with time, and hence some deterioration in terms of bandwidth caused by the introduction of a new pole do not cause any significant problem. That's it for my presentation of the project. Thank you.